Our fourth speaker, Mihai Vlad, is in charge of the commercial strategy for the machine translation division at SDL. He is an entrepreneur and a technologist with background in data sciences, marketing, sales, business and product development. Specifically, Mihai has a deep experience in developing and selling machine learning in the cybersecurity field. He will now discuss neural machine translation, the toughest challenge in AI.
Morning, everyone. It was great to actually meet Alex. This used to be my previous passion, cybersecurity, but now it moved into something else, expanding more into the field of AI. So I wanted to share with you what SDL has done over the past 15 years and the lessons we've learned by trying to solve one of the toughest challenges in artificial intelligence, and that is translation. I think some of the lessons we've learned across this period can be applicable to everyone who wants to invest in a company that works in the artificial intelligence field. So first of all, let's start with what artificial intelligence is. And it is our common ambition to get computers to do what humans do naturally. So if we think we can find our way to get to this event, we can drive a car, we can identify faces, and this is what artificial intelligence started focusing on. So we tend to use these technologies every day. We use Google Maps. That's a searching and planning problem. If you have a Tesla and you have a self-driving car, all the technology that is able to identify shapes and stop signs and stop the car, that has to deal with image recognition and probably facial recognition. And if you think about it, those are, and if you look at robots and seeing Boston Dynamic robots doing backflips, this is also something they were trying to get machines to do, to emulate what humans are doing. But there is something very unique about humans. If you think about it, we have animals who are better at navigating. If you think of dolphins, we have animals who have better vision than what we do. But what makes us unique, what is special about the humankind, is the fact that we communicate to one another. So when language was developed, this is what ultimately spawned what's called the cognitive revolution, and that sits at the basis of our collaboration. And it's an incredible feat. So Stephen Hawking was saying that mankind's greatest achievements came from talking, and our greatest failures came from not talking. So ultimately, language sits at the crux of what makes us unique. So that's why in artificial intelligence we have one other field which deals with language, and it's called natural language processing. And it's been from the dawns of artificial intelligence. So every time when you're thinking of speech recognition, that's artificial intelligence focused on language. Every time when you're typing a search on Google and you say, where is the closest, and you see the autocomplete, that is called language modeling. Every time when you're trying to get an automatic summary for a document that you don't want to read, that's again a technique called summarization that applies to the text being given. But one of the hardest ones is machine translation, and sometimes we take it for granted because we might be using it every day. But if we think about it, it's incredibly hard to ask a machine to somehow extract the meaning of what we say, understand that meaning, and transpose it into another language. If we think about it, like every word we say might have different meanings. So how can then we ask a machine to be able to understand that meaning and then be able to transpose it into not one language, but multiple languages? So there have been many attempts to solve this problem. The first approach actually started in 1949 with a gentleman called Warren Weaver. And Warren Weaver suggested that we approach this problem as a cryptographic problem. So instead of thinking that if you're looking at the Russian text, it's Russian, let's just imagine that it's English text that someone encrypted with a Russian code. And our job to extract the meaning or translate the text is nothing other than decrypt this language. A beautiful story. Unfortunately, we didn't have the computing power in 1949 to solve it. So our first attempts start in the 1950s, again focusing on Russian, and we had to use rules. So we built dictionaries. This was the Roosevelt experiment. We built dictionaries, a few grammar rules, and we were saying if this word appears there, then we translate it this way. If it appears in another part of the sentence, then probably rotate the order of the words. Now you can imagine that just in between Russian and English, there are so many complexities and subtleties just to get the fluency right that it was almost exhaustive to encode all these rules. And we might laugh about this approach, but it's the way we program computers even today. We still say, if this happened, then that should happen. So unfortunately, this technology lasted up until the 1990s. And as I mentioned, it's incredibly hard to get these computers to take all the inflection of language. So here I'm just taking a Russian word that ultimately has 12 variations or 12 inflections, depending on singular, plural. If we're taking gender, it just gets more complicated. And the whole word order is just mixed all over the place. I'm not sure if anyone speaks Russian, but they can attest to the free form of the Russian language. So then someone in the 1990s, almost like 40 years after, came up with this idea, said, you know what, let's forget about the rules. This is not going to get us anywhere. It doesn't scale. We have to replicate this in between every language. We have to redo the work and consider the 5 rules and 40,000 exceptions that appear in between 2 languages. So then they said, you know what, how about we actually let the machines learn these rules by themselves? How about we expose these algorithms to data, and we hope that they will learn the links in between the languages. So the data, when it comes to trying to get an algorithm to learn to translate, is nothing other than what's called parallel text. So if you're going to European Union, a law, it's most probably going to be written in English, then in French, and in all the other 17 languages. And that could be training data for the algorithms to identify these unique patterns in between the languages. And interesting, so what happened here was the first dawn, or it was the dawn of using machine learning to solve for machine translation, to let the machines learn from existing data how to solve for the problem. Interesting bit of trivia, this happened in the 1990s, and one of the key researchers to this approach was a researcher at IBM. His name was Robert Mercer. So he became then the gentleman that worked at the Renaissance Fund, developed the Medallion product, which ultimately generated roughly on average 70% return every year. So it's considered one of the best hedge funds in the world. So what's happening is that the same principles of machine learning were applied to finance, and the same analysis of text and analysis of numbers started to be applied in language. But it all started with the gentleman actually working, trying to solve for machine translation. 10 years after, it took us 10 years to actually productize the system. So this is where the history of SDL starts. We were able to take all this research and build a product that could be used and have someone be able to translate using a machine. But then everything evolved, and right now, just maybe 2 or 3 years, we've evolved the algorithms, and right now we're using these things called neural networks. So neural networks are nothing other than just another architecture for building a machine learning or to apply a machine learning approach. And what you're looking at here is just these concepts of neurons. These neurons are nothing other than just getting numbers or sequence of numbers multiply with one another. And if you're thinking of it like, this looks like magic, like how exactly can we just multiply numbers and translate from one language to another? And the secret behind this new phase is that we get words to be transcoded into numbers. So every word here, like die Proteste waren am Wochenende eskaliert, sorry for my German, every word becomes a sequence of numbers. 500, somewhere in between 300 and 500. So every word is being represented by a 500 dimension vector. So not just the 3 dimensions we have here, but by 500 dimensions. And once you start to explore this multidimensional space, something amazing starts to come out of this. The fact that if you're trying to draw a line in between the word man and woman, it will be exactly the same length and exactly the same angle within this multidimensional space in between king and queen. So hang on a second, what's happening here is somehow the machine is able to somehow mathematically describe the relationship in between words. And no one programmed this. This just emerged from the machine looking at this parallel text. It gets better. If you're looking in between the relation between king and queen, you're going to see a similar set of parallel lines in between the word kings and the word queens. So interestingly, again, without programming the algorithm, we're able to capture the the context of plurality or having the plural. And then it gets even better. You're actually able to look into a three-dimensional matrix, and you're going to see similar relationship between the word Sarkozy and France, Berlusconi and Italy, Merkel and Germany. Again, no one trained the system to do that. Just these features emerged from by training the algorithms and constantly improving for error. So we're going back to where we started. In 1949, 69 years ago, someone came, or Warren Weaver said, how about we're trying to solve the machine translation problem with numbers? Well, now we can. And interestingly, 69 years after, if we're looking into the guts of a machine translation system, you're going to see something that's called an encoder and something that's called a decoder. So what's happening here is that all these words are actually converted into numbers, and the meaning is captured here within this part of the system. And once a sentence is read, words start to be spread here in between these neurons, and then another translation can occur by iterating word after word. And again, what's happening here is just multiplication of numbers. So let's see how this looks. We're going to run a bit of a test, and to do that, we're going to refer to another code breaker in the Second World War, someone who's considered the father of AI, and he coined this term of a Turing test to figure out whether a machine can be easily distinguished from a human. So we're going to run through a few translations, and your job here is to determine whether this translation was made by a human or it was made by a machine. So the first one will be this. So even if you don't know Russian, just focus on the English translation. So I'll let you read this and let me know whether you think who thinks this is a human translator behind this? Not many people. How many people think this is a machine? Very good. Spot on. This is a machine. I'm not going to name the technology and the player behind this, but it's definitely a machine. Next one. Let's look at this. In the capital of Yemen, Tusana. So this is also definitely a machine because no human translator would actually repeat words. So this is when the machine is actually tripping up. Let's look at this one. What do you think? Is this a machine or a human? Who's up for a machine here? Very good. Who's up for a human? It's a human, actually. It's a human translation. Two more. Let's see about this one. A lengthier segment, so the rocket launch at a steep angle. I'll let you figure out if this is a human or a machine. There are some giveaways there. Who's saying this is a human? Very good. Roughly half. Who says this is a machine? It's actually a machine. Let's look at the more complex one. This is definitely a lengthier sentence. The BMW 2 Active Tourer Series is a place for you, anyone, etc. Definitely more complex. Is this a human? This is a machine. So how come you change your mind in the span of just a few, like 30 seconds? This thing took 69 years. This is actually a machine. This happens to be our own technology, but it could be every other state-of-the-art neural machine translation. But if you're looking at the feat of actually, if we just step back a bit and we think about it, we are able to take a sentence or a segment in Russian and are able to generate fluent translations, and I can guarantee it's the right translation, this one, and be able to present it so fluently. I mean, this is absolutely impressive, but what's unique about this thing is you don't know if the translation is actually good or bad. There is no objective metric that says this is 96% accurate, like in the case of speech recognition. If I say this, and a speech recognition algorithm will have ultimately to say, if I say this, everything else is wrong. When it comes to translation, everything could be considered a good translation or a bad translation. These are the challenges we've got. So in essence, this technology brought us 30%, or to the industry, 30% improvement in 2017, and in 2018, roughly 25%. To put this into context, if you were able to improve the technology at a rate of 1% or 2% per year, you would have gotten a PhD for the past 10 years. In the last 2 years, the quality increased massively. So then ultimately, why why is SDL and why are all the other companies investing in machine translation? Because ultimately the content is exploding and we want to communicate to one another, and content is becoming the lifeblood of every industry. As the previous speaker mentioned, we want to personalize experiences, we want to bring customers, we want to interact with customers, not in their own tone, but also in their own language. This is the best personalization that you can have, is actually speak to your customer in their preferred language. Then we might take it for granted here that the majority of the people speak English, but outside of this world, outside of this country, customers prefer to be spoken with or consume this information in their native language. So I'll share with you some of the use cases where machine translation is being used today. You may imagine that you're communicating with a colleague of yours in China and they send you a proposal in Chinese. What do you do with that? Do you actually paste it on a free translation tool to see what's happening? What if it contains something sensitive? So probably you would want to pass it through a machine translation system. Equally, a customer of your company, as you're trying to go further and globalize, they might want to speak to a customer representative, but the customer speaks German and the customer representative speaks English, and it's only the customer representative that speaks English that's who is available. What you do then? What you can do is you can use real-time machine translation to broker the communication, and the customer would not know that he's actually being spoken to by a person who doesn't know German. And then it can be expanded. You can use it into chatbots, but ultimately machine translation is this bridge that is enabling a lot of commerce or a lot of communication in between actors. If you're thinking you have an e-commerce business and you want to go into other markets, one of the approaches would be to translate all the content using human translation, or you can take part of that content and translate it directly with machine translation. So ultimately what machine translation does is able to add this multilingual factor and expand your business or expand the reach of your business beyond what you can do with one single language. And it could be applied, imagine if you're in a legal dispute and you have to crawl all the information, all the emails within a company to build your case. There might be that those emails and the documents are not in English. What do you do with the billions of words that have been produced, let's say, for a lawsuit over the past 5 years? You can't translate all of them manually, but what you can do is actually pass them through a machine translation system and then run your e-discovery system. So we're seeing this is how our customers are using these tools. But in essence, I wanted to also make a point, something that we take for granted. Just because the technology is available out there in the cloud, it doesn't mean that we should take all these information that's sensitive to us and just paste it and then just get a translation just because we think it's free. Because what we've done by doing this, not only did we break the GDPR rules, but we've also given away all the sensitive information, all the IP of our company. By doing this, these services are offered for free in return for the data you put into the service. So our proposition is all about translating securely and ensuring that enterprises and government organizations do this in a secure manner. Now, we've learned something interesting is sometimes we laugh about free translation tools, and you've seen just within the span of 30 seconds how quality has improved, but the reality is a bit different. There is no such thing as a perfect translation solution, as there is no translator who is able to translate legal documents and tomorrow be able to translate financial documents. They need to be specialized into a specific domain. That's why you will see a generic quality that is kind of like changing in between vendors. But when it comes to a specific domain, into let's say a financial domain or to patents domain, you will have to adapt the technology to suit that specific domain. So in summary then, what I wanted to share with you, and then we're going to go to the lessons learned, is that when it comes to artificial intelligence, there is a big focus on language, and it's one of the hardest problems to solve. Some people say that it's probably harder to build a self-driving car than to build a perfect machine translation system. That's why machine translation is considered by researchers something called AI complete. Once we are able to properly get this problem sorted, then we would have achieved these rarefied stages of having solved artificial intelligence and getting computers to do what what humans do. I wanted also to make a point that if artificial intelligence and, let's say, machine translation specifically is the what, the way we solve these problems could be with rules, get to program all the grammatical rules, or we can let the machines learn from the data. Therefore, machine learning is the how. So every time you want to separate these two, artificial intelligence, the whole blob, machine learning is ultimately the how you're trying to solve these problems. And then if you're thinking about investing in companies that, or who operate into the machine learning or artificial intelligence field, there is a great quote from Andrew Ng that I think might help you identify or help you navigate this field. So Andrew Ng was one of the key researchers behind neural networks, but he was also the head of AI for Baidu being the Google of China. And he said in order to achieve competitive advantage in artificial intelligence, you need four things: data, talent, hardware, because you need to compute lots of data, and algorithms. But the importance of them is actually very different. He poses the fact that having access, or if the company has access to good and high quality data, they have a competitive advantage. So always ask yourself, is the company truly getting access to real data to use it for machine learning to train those algorithms, or not so much? That's why Facebook has a lot of value, because they have access to a lot of data, our data. And when it comes to algorithms and hardware, these things are getting commoditized and open source, but getting true talent to adapt the system and customize those systems is fundamental. That's why there's a war on talent in the Silicon Valley and here in London to get proper researchers to understand this, because it's not like electricity. It's not like you're plugging something in the socket and stuff miraculously happens. You have to wrestle with the data. It's a completely new paradigm. So whilst it gives you all those advantages, you have to work at it. So always focus on companies that have either access to data and have right talent. And last but not least, I wanted to say something in closing. We are seeing this debate in between the human and the machine. And in what you've seen here, like this test, the conclusion might be that we've achieved human quality. Because you've seen that translation, the conclusion could be, that's it. Machines are able to translate. We don't need any other support from humans. But that's actually not true. In order to get perfect translation, a translation that you put on the label of a drug, or something that supports a legal contract, or something that you're able to put on your website, machine translation might not be good enough to solve this problem. That's why at SDL we actually have a huge business just working with professional translators to help us get into those unique services. And what machine translation does is actually helps those human translators be more productive and be more efficient. And last but not least, I'll leave you with one quote from Geoffrey Hinton. So he was probably one of the fathers of neural networks, and everything that we think of right now in deep learning and image recognition and everything, we're almost here because of the work of this gentleman. And having seen this advancement of neural networks and artificial intelligence and all his work being used by us and having taught by us, he was asked, now that you've achieved nirvana, now that you've achieved your lifelong dream, can you retire? Is your work done? And he said, no, actually, I still wanna get these machines to get a proper translation done perfectly or done successfully. But we think we are still almost like 10 years away, because we need a data set that's probably roughly 1,000 times bigger than we have, and there's still work to be done. So we've put on the effort to do this for 15 years. We're committed to do this for the next foreseeable future, and I think it's a challenge that will keep us occupied for a long time. So thank you so much for listening.
I might just ask the first question then, is how do you actually measure the accuracy of the translation? Does everything that comes out of the computer have to be checked by a professional translator?
It depends a lot on the use case. So in the case of when you're building the technology, there is an algorithmic method called BLEU, and what it BLEU, and what it is you provide the machine with a text to translate and a golden translation done by a human, and then you measure the difference. But as I said previously, it's not perfect, because maybe a human translator might choose a different word order for their translation or pick up a different meaning. So it's not accurate, but it trends really nicely. It helps you indicate whether your technology is going upwards. The other tests we do every time we release the technology on every of the language combinations, we get professional translator to run a blind test. And you expose them to a human translation and a machine translation. And then there's an error rate, and it's called Likert, and it's called, so there are human metrics and algorithmic metrics. And then I said it depends on the use case, because let's say in the case of a travel website, they want to get more traffic from, let's say, visitors in China. The quality doesn't matter that much as long as more people spend time on their website. So the quality has to be linked with the business value of what the technology brings.
You showed how each word could get mapped to a vector. Could you do the same with direct speech? So, translate direct speech without having to transcribe it?
Not at this stage. So the state-of-the-art technology is it takes the phonemes, converts them into text, and then there's a language translation, and then speech is being generated. But there is some research to try to encapsulate the phonemes as a vector, but it doesn't work too well. And actually, people in machine translation are always a bit frustrated with the speech recognition guys, because they're always like a bit further ahead, and they're definitely evolving much, or they're 5 years ahead of translation. The quality is, right now, the quality of speech recognition is better than the human speech recognition. You're at, I think, 96% quality. So, but still, state-of-the-art, transcode in text, translate, and then extract the speech again.
Is there much in it between language generation and translation? I know you have, these sort of auto-writing articles and stuff like that, and that which have been around for a while. I mean, we can still recognise them, but they're a lot better than they used to be. And I'm just wondering, is this a step beyond that?
It's actually, I'm just going to go very quickly back here. If you're looking into, I'm just going to be very brief here. When it comes to machine translation, actually half of the problem is generating language. You encode it at first, and then half of the work is generating fluent language. So machine translation, that's why it's considered AI complete, because it encapsulates all these things. Now, there are, the field is called NLG, and there are some companies and some specific use cases. Like, as an example, if you want to generate the financial report, and you don't want to write the same thing over and over, and you have the data with you, you can actually take the data and generate human readable text. The secret behind this is that the majority of them are actually templates. And there's not much machine learning. So you're going to see, I think it will improve and it's going to get better. The technology exists, but the use case is that it's almost like, I would recommend you, if you want to have a bit of fun, is just, I may send you an email with a really cool blog called The Unfair Advantage of Recurrent Neural Networks. So what they've done is they train the machine on the Shakespeare plays, and then get the machine to generate Shakespeare-like text. And it is Shakespeare text. It's hard to distinguish it, but it doesn't make any sense. Same thing applies. They train it to generate scientific papers, and you're almost like reading a scientific paper, but it doesn't make any sense. So the technology is there, but right now it's templated, and people in the industry laughed because we know that it's being used for financial reports and for horoscopes. So that's I'm not joking, and weather reports. Okay.
Thank you, Mihai. We'll move on to the next speaker.
Thank you.